Okay, more of this again. So let's see, last time we covered mostly NOT gates, also known as inverters, and NOR gates. So let's see, I'll go ahead and start by covering a NAND gate. So a NAND gate is also pretty straightforward. You have essentially 3 transistors stacked on top of each other like this. And that's ground as usual. And these 2 MOSFETs at the bottom, their gates become A and B, so the 2 inputs into the AND gate become the 2 inputs are the gates on those 2 bottom enhancement mode MOSFETs. And the top is the same thing that we've already seen before. It is a depletion mode MOSFET, the gate of which comes and crosses over like that, and this becomes the output. And as usual, this is your positive input. Yes. And this is indeed a NAND gate. And so the basic idea is if if both A and B are on, then that turns on these 2 MOSFETs that allows the output to be pulled down to ground. If either A or B are not on, then this segment is essentially closed off and out cannot go low and it will remain high. So the truth table for a NAND gate looks like this. So basically, in an AND gate, 1 and 1 would give you 1. So in a NAND gate, that gives you 0, and everything else gives you 1. Yeah. So basically, as you can see, like I said, if A and B are both on, then that pulls the output down to 0. Otherwise, there is no path to ground, and so it stays high. It stays 5 volts, assuming 5 volts is your high logic position, which it is in TTL. So it's an AND gate, and of course, again, if you want to make an AND gate, then you just take this and run the output through to a inverter or a NOT gate, and then the output of this becomes AND. Alright, not too bad. So far so good. Let's see, what else do we have? Okay, next let me go ahead and do an exclusive OR gate. That should be fun. So the way that you do exclusive OR, I guess there are a few different ways of doing it. The way that the 6502 does it, if you look at the PDF diagrams, is it typically looks something like this. It has a structure that looks very similar at first to a NOR gate. So let's see how. Yeah. So these 2 at the bottom are enhancement mode MOSFETs. This is a depletion MOSFET, and as you can probably guess, this up here is your positive input, and yes, the gate for this is something I can't draw. Hold on, let me try that again. I can't draw straight. Oh no. Let's try this again. So that is the gate, and this becomes your output. So what we are missing from this diagram, and which I will attempt to draw, is what you do with the inputs. The input on one side actually takes the input from a NOR gate. I'm not going to draw the proper NOR symbol. I'm just going to draw it as a box, even though if you wanted to do it properly, you'd obviously draw the NOR symbol, which looks like that. What the heck, since I've already drawn it, why don't I go with that? Let's go with that just to make it look proper. And so what you end up doing with the NOR gate then is this NOR gate actually takes the inputs of A and B. So basically, inside the 6502, what actually happens is it uses, like, it borrows the output from its own NOR gates and pipes them into this side of its XOR gates. So this is one input into the XOR gate. I'll put XOR for exclusive OR up here, even though this isn't quite done. And on the other side, what it does is it uses the input from its AND gate, or from its NAND gate. So basically, over here there is, on each XOR gate inside the 6502, there is an inverter like that. And then there is, just as it borrows the NOR gate on this side, it borrows the output from one of its own NAND gates. And then this takes the inputs, of course, of A and B. And that is a NOT gate. So basically, let's see, what am I missing? Did I forget anything? No, it uses the NAND gate here, and then it turns it into AND by doing that. I think I got everything. Very nice. Okay, so the truth table for XOR, of course, looks like this. It's exclusive OR, meaning if one or the other of the inputs but not both, then true, output of 1. So these give you 1, and if both of the inputs are the same, then you get a 0. So the way that this works is if A and B are both low, then the NOR gate turns on, and that activates this input here and pulls the output down to ground. So basically, if you have this case here, where A and B are both low, then that activates this NOR gate, and that pulls this output down so that the output goes down to ground. Conversely, on this side, this has the net effect of being an AND gate, because it's a NAND gate that goes through an inverter, so that basically gives you AND. I'll just circle that whole thing and just, why don't we just say that's AND, because that's essentially what it is. So, so that gives you then this case, and once again, if 1 and 1 are, you know, both true, then you get a that activates this MOSFET here, and that again pulls the output down to ground because this MOSFET is now conducting to ground. If neither of those are the case, then this doesn't turn on and this doesn't turn on, and then the output stays high, and that gives you these two cases here. And of course, the 6502 doesn't do it internally, but if you want to make this into an XNOR gate, a not exclusive OR gate, then you can, on the output line, just stick an inverter like that, and that makes it an XNOR gate. Okay, that's it. So that's the different types of gates. Did I miss any? No, I think that's it. I think that covers the major types of gates. So let's see. Let me do something else. Let me draw. What was the other thing I wanted to draw? Oh yeah, the outputs. The outputs that are used inside the 6502 diagram are very simple. Basically, they're typically drawn. I'm gonna borrow the ones that are used for the data bus. And the data bus is bidirectional, but I'm just going to draw the output portion of the data bus. So the data bus is all kind of stacked up on the left-hand side of the diagrams. And this big black dot is the actual pin. Actually, it's not the actual pin, I guess. It connects to the pin. I mean, internally it's a pad. It's a a square of conducting metal inside the chip package, and then there's a very fine bond wire that actually connects it to the to the actual huge pin that's on the outside of the package like that. You won't see that on the diagram, of course, but basically you can think of it as being the pin because it connects directly to the pin. So electrically, for all intents and purposes, it basically is the external pin of the data bus. So the way that the data bus outputs, and actually all the other outputs in the diagrams look, they look like this. So you have two MOSFETs, like that. They are both enhancement MOSFETs. It's your positive supply. And that's it. So basically, this allows you to set that pin to be either high or low. If this MOSFET is turned on, then obviously the pin is connected to your positive supply and you get a 1 out. And if this one is turned on, then obviously the pin connects to ground and you get a logical 0 out. So you can say, I don't think this is quite the right terminology because this is more terminology you'd use to apply to a latch. Or actually, is this the right terminology? I don't know. Maybe it is, maybe it isn't. But you can sort of think of this as the set pin that sets the output, meaning it turns it on. And this, if you're using that terminology, then the counterpart to that would be this would be the reset pin to set the output to 0. Or you can just say that this is the 1 input, sets that pin to be a 1. And this is 0, it sets that pin to be a 0. That's really it. That's how the outputs work. On the data bus, since they're the pins are bidirectional, there's also another line that kind of snakes down like this and goes to another section, which I'm not going to draw here for now. But that's basically how the outputs work. I believe that's how the address bus pins look, if you look at how the address bus works inside the 6502. Okay. Looking good. I think that's it. That's pretty much all the diagramming I wanted to do for right now. The other thing, since I'm making this video, one other thing that I wanted to really quickly mention was I have in my notes, let me just type this out. Let's make that a little bigger. The one thing that I wrote in my notes, and it would help if I made my text black so that we could see it instead of white, is the sum bit, how to calculate the sum bit. And hold on, let me make that text a little larger, why don't I? There we go. The sum bit is A, wait, no, put in brackets, A XOR B, and then that whole thing XOR the carry bit. So, when you're doing addition, you have A and B, although it might help if I knew my alphabet and knew that A comes before B. You have A, you have B, and then you have a carry bit. When you're doing addition, of course, you know, sometimes you carry. And so, let's see, how should I draw this? I don't know if I'll draw out, I guess I can draw out the whole thing. So basically you have 8 different possibilities. That's 3 bits, and with 3 bits you have 8 different possibilities, right? So it can be like that, can be like that, can be like that, can be like that, and I'm going to run out of space. Alright, I'm not going to draw all 8 of them, but this is 5. So basically the point is that the sum bit for doing these calculations should be this XOR that, and then whatever result you get out of that, XOR that with the carry bit. So for example, this XOR that is 0, and that's also 0, so the sum bit for that is 0. This XOR that is 0, but that XOR this is 1, so the sum bit is 1. And same thing here. Basically, if one of these is 1, then the output is 1. And if 2 of these are 1, then you know this XOR that is 1, but this XOR that is 0, so the sum bit is 0. And also you would carry the I'm not showing the result of this, the carry result of this operation, but there would be a carry bit out of this. So basically, if two of these are 1s, then the sum is 0 when you have a carry bit, and this, this would give you a sum of 1. The other case is where all 3 are 1, in which case you would your sum bit would also be 1, because this XOR that is 0 actually. Yeah, 1 XOR 1 is 0, but then 0 XOR 1 is 1. So the sum bit would be 1, and you'd also have a carry bit. So there you go. That's how you calculate the sum bit. Fascinating, I know. Okay, that's all I wanted to discuss for now. I'll probably, I may make some more follow-up videos explaining some more stuff about how the 6502 works internally, but that's all the gate types for now. So I hope that at least somebody found this interesting, and if not, well, thanks for watching anyhow. I'll talk to you folks later. Bye-bye.